In this chapter, we will learn shortcuts to finding the derivatives of various functions without having to use the limit definition of a derivative. Recall that the derivative of any function tells us the slope of the tangent line to that curve, and it is a function itself. Example 1 says find the derivatives of the following functions using methods that we have seen so far in this course. In part A, we have y equals 1. If I were to graph that, that would be a horizontal line. Here's my y-axis, here's my x-axis. If I were to take the slope of the tangent line anywhere along this horizontal line, it would essentially be that line itself, and the slope of a horizontal line is 0. So recall that there are a couple of notations that we can use for the derivative. We can say that y prime is equal to 0, or we could say that dy dx is equal to 0. So either of these work for part A. For part B, we have the function y equals x. If I were to graph that, here's my y-axis, here's my x-axis. The graph would look something like this, where it went through the origin. And again, if I were to take the slope of the tangent line at any point, because this is linear, it would essentially be that line itself. And the slope of that line is 1. So we would say y prime is equal to 1, or we could say that dy dx is equal to 1. Let's move on to the next part. All right, so we're on part C, and our function is y equals x squared. We would like to find the derivative of this function. Now, something that you'll notice in this function is if I choose an x value, and I draw the tangent line at that x value, and then I choose a different x value and draw the tangent line there, the slopes of these tangent lines are going to vary, and so that means that our derivative function is not a constant. Same thing here, if I drew its tangent line, it would be this horizontal line there. So, at least with the methods that we've learned this far, in order for us to find the derivative function, we're going to need to use the limit definition of a derivative. That is, y prime is equal to the limit as h approaches 0 of y of x plus h minus y of x all over h. Let's go ahead and fill this in for our function. So we have the limit as h approaches 0 of x plus h quantity squared minus x squared all over h. Now what we want to do is we want to expand out x plus h squared so that hopefully we get some simplification in the numerator. This is equal to the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. Luckily, we get that x squared and minus x squared will cancel out. And the remaining terms have h's in them, so we can factor out an h, leaving us with 2x plus h all over h. These will divide out to be 1, and now we can use direct substitution. If we do that, we get 2x plus 0, and so finally we have that y prime is equal to 2x. In part D, we are looking at the function y equals x cubed. Once again, if I choose some arbitrary x value, if I take the tangent line there, or somewhere like here, notice that these are not going to have the same slope, and so we have to once again use the limit definition of our derivative. So we find that y prime, and remember you could say y prime or dy dx is equal to the limit as h approaches 0 of y of x plus h minus y of x all over h. This becomes the limit as h approaches 0 of x plus h quantity cubed minus the original function, which was x cubed, all over h. Once again, our goal right now is to expand x plus h cubed. Doing so will give us the limit as h approaches 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. X cubed and minus x cubed will give us 0, and then every remaining term in the numerator is going to have an h in it. So we can factor out h. From here we can divide out the h's in the numerator and the denominator, and now we can use direct substitution. We would get 3x squared plus 3x times 0 plus 0 squared, which if we simplify, we just get 3x squared. So this is our derivative function for y equals x cubed. Did you see a pattern on the previous page? It turns out that we have this thing called the power rule, which says if n is a real number, then the derivative of x to the nth power is equal to n times x to the n minus 1 power. So let's complete the proof of the power rule below. We start the proof by saying let f of x equal x to the nth power. Using the limit definition of the derivative, we have the following. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So we've talked about this previously. This thing here is the difference quotient. And we know that our function is x to the power of n, so if we replace x plus h, we get x plus h to the power of n minus x to the power of n all over h. Now what we want to do, just like we've done previously, is we want to expand x plus h to the nth power. Doing so gives us this very long expression here inside of these large brackets. So expanding us gives us this expression here, and if you're a little bit confused about where the coefficients are coming from, so notice we have, for example, n times n minus 1 over 2. Here our coefficient's n. Here our coefficient is n times n minus 1 over 2, n, and then here we have a coefficient of 1. If you are not quite sure where those are coming from, one way that you could come up with those is by kind of taking a look at Pascal's triangle. And in Pascal's triangle, when you're looking at an entry in a row, you are essentially choosing a combination. And so if you don't know what that is, that's not too much of an issue. Don't worry about it too much. But the important thing that we want to understand here is that notice that we have x to the nth power and minus x to the nth power. And as a next step, we have the limit as h approaches 0 of, and what you'll notice now at this point is that every remaining term has at least one h in it. And so we can factor out h, and that will leave us with n times x to the n minus 1 power plus n times n minus 1 over 2 x to the n minus 2 power times h plus dot dot dot, and then the second to last term we would have n times x times h to the n minus 2 power, and then plus our very last term here, when we're factoring out an h, would leave us with h to the power of n minus 1. This is all over h, and just like we've seen on the previous page with those 4 examples, the h's will cancel out. And now I can just kind of copy this thing down. At this point, I can use direct substitution. And notice that every single term except for the first one is going to disappear because I'm plugging in h equals 0. The first term here, because we factored out that original h, does not have an h in it, and so we will be left with n times x to the power of n minus 1, and then plus a bunch of zeros. And so we have shown what we set out to show, and I'm going to put my little mathematical proof symbol here. You'll notice that I put one here as well. That's a more common mathematical proof symbol, just the square, but I like this one. This is the one that I was taught when I was in high school, so that's the one I tend to use. All right, let's go ahead and move on to example 2. Example 2 says evaluate the following derivatives. Recall that x to the power of m over n is the same thing as the nth root of x to the m power. So let's start off with part A here. I want to take the derivative of x to the 11th power. And before we learned about the power rule just now, if I wanted to use the limit definition, that would be quite a pain because I would have to expand x plus h to the 11th power, and I don't want to multiply that out 11 times. So this makes our life so much easier now that we have the power rule. If I follow the power rule, then I can bring my exponent to the front and multiply it to x, and then my new power of x becomes 11 minus 1, which is 10. So this is my answer for part A. For part B, the derivative of x to the 200th power, again, I will bring down the 200, multiply that by x, and my new power will be 1 less. 200 minus 1 is 199. So there's my final answer for part B. Look how quick that was. All right, for part C, we are taking the derivative with respect to y. That just means that our variable that we are looking at is the y variable. And right now I have 1 over y to the 7th power, which is not of the form some variable to a number exponent, but that's okay. We can rewrite this as the derivative with respect to y of y to the negative 7th power. So now it's in the form that we want it to be, and we can use the power rule now. I can bring down my power, and then negative 7 minus 1 is negative 8. Please be careful not to say that it is negative 6. And there's our answer for part C. Now, if we wanted to, we could rewrite this as negative 7 over y to the 8th power. I would accept either of those as a final answer. All right, for part D, we have the derivative with respect to x of, now I'm going to rewrite this thing so that it has a fractional exponent that is the same thing as x to the power of 5 over 6. Now I can use the power rule. So I'm going to bring down my power, and then we have x to the power of 5 over 6 minus 1 is the same thing as 5 over 6 minus 6 over 6, and that is equal to negative 1 over 6. And there is our derivative for part D, and that concludes example 2. Example 3 says find the equation of the tangent line and the normal line to the function y equals 1 over x to the 5th power through x equals 2. A normal line is a line that is perpendicular to the tangent line. All right, so what is it exactly that we're doing here? Well, if I'm finding the equation of the tangent line, then at x equals 2 on this function graph, I'm trying to find the equation of this line here, and let's go about doing that. So our function is y equals 1 over x to the 5th power. I don't have the tools to take the derivative of that unless I use the limit definition of a derivative, which is going to be quite painful. So I want to rewrite this as x to the negative 5th power so that I can use the power rule and I can take the derivative of that. So if I use the power rule, I bring the power down, and then my new power is negative 5 minus 1, which is now negative 6. And that is the same thing as negative 5 over x to the 6th power. Now what I'd like to do is I'd like to find the slope of the tangent line when x equals 2. So I'm going to evaluate this for x equals 2. That's going to give me negative 5 over 2 to the 6th power, which will simplify to be negative 5 over 64. Now, the other thing I need is I need a y-coordinate on my function graph for when x equals 2. So in my original function, not y prime, but y, I'm going to evaluate y of 2. That's going to be 1 over 2 to the 5th power, which is equal to 1 over 32. So this y value right here is 1 over 32, and the x value is positive 2. So let's talk about the normal line. Not the normal line, the tangent line. And I'm going to put it in point-slope form. So that's going to say y minus 1 over 32 is equal to the slope that we found, negative 5 over 64, times x minus 2. And that is our tangent line in point-slope form. Now I'd like to find the equation of my normal line, which is perpendicular to the tangent line, and it would look something like this, and I know that it's normal or perpendicular because it forms a 90-degree angle with my tangent line. And if you don't remember, the way that you get two lines to be perpendicular is their slopes have to be opposite reciprocals of each other. And so here in my tangent line, my slope is negative 5 over 64. The reciprocal of that, the opposite reciprocal of that, is 64 over 5. So we take the reciprocal and we also change the sign from negative to positive. And we still see here that our normal line is still going through the point 2 comma 1 over 32. And so our equation is y minus 1 over 32 equals 64 over 5 times x minus 2. So here is the equation for our normal line. The constant multiple rule says if c is a constant and f is a differentiable function, then the derivative of a constant times a function is equal to, I can pull out the constant and then just take the derivative of the function and multiply those things. Let's look at an example of that in example 4. I would like to find the derivative with respect to x of negative 3 over 10 times x to the 15th power. Negative 3 over 10 is a constant, so according to this rule right here, I can pull out the negative 3 over 10 and multiply that by the derivative with respect to x of x to the 15th power. From here we get negative 3/10 times, we can bring down the power, and our new power would be 1 less, which is 14. And these two constants I can multiply together. That's going to give us, let's see, I'm going to rewrite this as negative 3 over 10. I'm going to rewrite as 5 times 2. And then 15 I will rewrite as 5 times 3. And then these 5s will divide out. And that leaves me with negative 3 times 3, which is 9, or negative 9 over 2. X to the 14th power. And so here is our derivative. All right, so here are two really helpful rules. They are called the sum and difference rules. If f and g are differentiable functions, then the derivative of f of x plus g of x is equal to the derivative of f of x plus the derivative of g of x. And same goes for if you're subtracting two functions, then you could split that up into two separate derivatives and then subtract them. So let's see how that comes into play in example 5. Example 5 says find the first three derivatives of the function f of x equals x to the 4th power minus x to the 6th power minus 6x squared plus 4x. And I'm going to say f prime of x, our first derivative, is equal to, I'm going to use the rules that we just learned to say that it's the derivative of x to the 4th minus the derivative of x to the 6th power minus 6 is a constant, so I can pull that out. And then 4 is also a constant, so I can pull that out. And now I can take each of these derivatives. So that gives me 4x cubed minus 6x to the 5th power minus 12x plus 4 times 1. The derivative of x is 1, so I'm just going to rewrite this as just 4. So here we have f prime of x. Now, I'd like to find the second derivative, which we call f double prime of x. I'm going to use the power rule on each of these terms again, and that's going to give us 12x squared minus 30x to the fourth power minus 12. And the derivative of 4 is equal to 0 since 4 is a constant. From here, we can find the third derivative, f triple prime of x. And again, I'm going to use the power rule on each of these terms. So 12 times 2 is 24. And then x, if I decrease the power by 1, my new power is 1, minus 30 times 4 is 120, x cubed. And then the derivative of 12 is 0. So here we have our first derivative, our second derivative, and our third derivative. Now, it doesn't ask for the fourth derivative, but if it did, remember that our notation for our fourth derivative is when it changes up and it starts to look like this, where there's a superscript of the number 4 inside a set of parentheses. And then that would give us 24 minus 360x squared. So that would be the fourth derivative. Example 6 says find the derivative with respect to r of this function here, and I want to rewrite the square root so that it's to the 1/2 power. And I'm going to separate the derivatives. Okay, so let's go through each of these and take the derivative by using the power rule. 1/2 minus 1 is going to give us negative 1/2. Our next derivative is 1, and then we have plus 2 times, if I bring the power down, that's negative 3/4 times r, and then negative 3/4 minus 1 should be negative 7/4. And the only thing is we can simplify 2 times negative 3/4. And 2 times negative 3/4 should be minus 3/2. And here is our final answer. Example 7 says, for what values of x does this cubic polynomial have horizontal tangent lines? I'm going to really roughly sketch a graph of my cubic polynomial. I can see that the leading coefficient is 1, which is positive. And I know that my degree is odd, which tells me that my end behavior is going to be down, up. And so let's say it looks something like that. I just made it up. And we are trying to find where this has horizontal tangent lines. Now remember, that occurs at any local maximums or local minimums. So let's say I have a local max here and a local min here. If I took the tangent line, notice that those would be horizontal. And another way of saying that is that those slopes of those tangent lines would be equal to 0. So I have my function here. What I'd like to do is I'd like to find my derivative function. And if I do that, I get 3x squared plus 6x plus 1. And if at those horizontal tangent lines, those slopes are 0, what I can do is I can set my derivative here equal to 0. And my goal now is to solve this equation, which is 0 equals 3x squared plus 6x plus 1. This is a quadratic equation. I would try to factor it. I don't think it's nicely factorable, so now I am going to use the quadratic formula. I have negative 6 plus or minus the square root of b squared minus 4 times the a value times the c value, all over 2 times the a value. So we have negative 6 plus or minus the square root of 6 squared is 36 minus 12 should be 24 over 6. Now I can rewrite this as negative 6 plus or minus. 24 has a perfect square as one of its factors, and that perfect square factor is 4, so the square root of 4 is 2. That's going to leave me with 2 root 6 over 6, and then I can simplify that by factoring out a 2 from the numerator. And then the denominator, I can rewrite that as 2 times 3, so these 2's will cancel out. And finally, I'm left with negative 3 plus or minus the square root of 6 over 3. And so it asks for what values of x, and these are the x values where we have horizontal tangent lines. And so it's kind of like in this picture, my graph is not accurate, but this could be one of the x values, and this could be another x value where we have horizontal tangent lines. Since we have negative 3 plus or minus, that gives us 2 x values. You might have learned about the number e, which is approximately equal to 2.718. Known as Euler's, his name rhymes with Euler's number. There are a few different ways that this number can be defined. Let's take a look at some of them. Of these 3 definitions, the one with the limit is the one that we kind of have an idea about because we learn about this in Calculus 1. I teach at a college on the quarter system, and so this definition here you would learn in Calc 2, and then here you would learn about this definition here in Calc 3. So it turns out when you take the limit as x approaches infinity of this function here, it's equal to the number e. What's so special about e? Well, one reason that we care about it is when we take the derivative of the natural exponential function, its derivative is itself. And so here I want to emphasize that the derivative of e to the power of x is equal to e to the power of x. Example 8 says find the following derivatives. I'm going to, in part A, split this up so that we have 5 times the derivative of x cubed plus the derivative with respect to x of x to the 1/2 power minus 4 times the derivative of e to the x power. So this is equal to 5 times 3x squared plus 1/2 x to the negative 1/2 power minus 4 times e to the x power. And then we can clean this up by multiplying 5 times 3. If I wanted to, I could also rewrite this as 1 over 2 times the square root of x. And we have this as our final answer. For part B here, I'm going to break this up into the derivative with respect to r of e to the r power plus the derivative with respect to r of r to the e power. Now the way that we're going to approach this is different, because here we have the natural exponential function. Instead of x, we have our input variable to be r, so its derivative is equal to e to the power of r. Now this second thing here, we have r, which is our variable, raised to a power of a constant. And so because e is a constant here, we would utilize the power rule. And so I would bring the power down times our variable r, and then my new exponent would be e minus 1. So here is our answer for part B. Example 9 asks us to find the derivatives of the following functions. Part A, we have, I'm going to break this up into the derivative with respect to y of e to the y plus 1 plus the derivative with respect to y of 1. Now this thing is a constant, and taking the derivative of a constant gives us 0. And then I also want to break up e to the power of y plus 1 using exponent rules. That is the same thing as e to the power of y times e to the power of 1, and then plus 0 from this 0 here. I'm just going to erase that. And e to the power of 1 is a constant, so I can actually pull this out and then multiply that by the derivative with respect to y of e to the y, which is just e to the y. So now I'm going to have e times e to the power of y, and if I'd like to write that more succinctly, that is the same thing as e to the power of y plus 1. So here is our derivative function for part A. So for part B, I've gone ahead and I've split these up, and this derivative is equal to e to the power of a, just because we're taking the derivative of the natural exponential function. And then in the second part, I can't use the power rule yet because we want to expand negative 2a plus 1 quantity squared first in order to be able to use the power rule. So altogether, we will have e to the power of a plus the derivative with respect to a of, if I multiply this out, that's going to give me 4a squared minus 4a plus 1. And now I can take the derivative of each of those terms individually by using the power rule. That will give us e to the power of a plus 8 times a minus 4. And then the derivative of 1 is 0, so we are done here. In part C, I've gone ahead and I've split up my derivative into the sum of two different derivatives. And in the first derivative, I'm not going to be able to use the power rule on that yet. So let's see if we can change this up. First off, I want to rewrite the square root as an exponent of 1/2. From there, I'm going to rewrite this and separate this into two different fractions. So I would have x to the 1/2 over x squared plus x over x squared, like that. And now we can simplify that even further, and we would have the derivative of, remember from exponent rules that if I have x to the a power over x to the b power, this is equal to x to the power of a minus b. So 1/2 minus 2, that will give me negative 3/2. And then x over x squared, that is the same thing as x to the negative 1 power. Now here, I'm going to split this up into e to the x power times e to the negative pi power, and then e to the negative pi is a constant, which I can pull out. So let's go ahead and use the power rule. This will be equal to negative 3/2 x to the negative 3/2 minus 1 would be negative 5/2. I'm going to bring down my power and then subtract my old power by 1 to get negative 2. And then plus e to the negative pi times e to the x. So we have negative 3/2 x to the negative 5/2 power minus 1 over x squared, and then plus e to the power of x minus pi. And there's our final answer for part C. For part D, we have the derivative with respect to v of this fraction here. I've gone ahead and rewritten the 7th root as v to the 1/7 power. And once again, I'm going to split this up into two fractions. So I have v to the 1/7 power over v minus 2v times e to the power of v over v. In this second fraction, I can divide these v's out. And so this will give me, in the first fraction, I can do 1/7 minus 1, so that will be v to the negative 6/7 power, minus 2 times the derivative with respect to v of e to the power of v. If I use the power rule, we have negative 6/7 times v, and then, let's see, negative 6/7 minus 1, that should be negative 13/7 minus 2 times e to the power of v. And here's our final answer for part D. And that wraps up this video. Thanks for watching.